So basically, I'm presenting extracting references from political speech auto-transcripts. So I had several hundred hours of speeches from the 2016 political campaign in the US, and I wanted to know, like, what are they even talking about? So it's, I tried a bunch of stuff, and I ran into this. This is from a paper that's about auto-evaluation of topic models, and he goes on to say that, the smaller the topic from LDA, the worse it is. And he goes on to say that with LDA, you can't really make super finely coarse topics to get, just like very specific stuff out. And it's complicated by a few factors, but this is basically what I would get these are the best, highest scoring LDA topics with a high number of K. So you get all these nonsense clusters, basically. So it basically proved that, it breaks down when you're trying to get real specific stuff. And especially when you have tons and tons of errors. So I just copied a huge chunk of a part of a speech. I highlighted all of the transcription errors. And then in yellow, we have, that's a Bergdorf, but that should have been a Bergdahl. So not only do we have these errors, but we're actually getting like some very critical references totally obscured, because there's like 50 references to Bergdahl, a single Bergdorf in this case. So you're never going to be able to get that single Bergdorf out with just LDA. So the high-level overview for how we're doing this is we scraped all of the auto-transcripts from Google, and Google uses a deep learning model to automatically transcribe things into many languages. We just use English. Then we pre-process it, just real simple, just basically tokenize on white space and lowercase. Remove like audience cues and stuff like that, because they do add all of that. And then we just built an embedding model. So I tried a few different ones. I tried just straight word-to-vec, and then I also used fast text. Fast text was chosen in this case because when they miss the transcription, it's usually pretty close. So it'll have like most of the letters right, but not all of them. So even if it's a different word, it doesn't really matter, because just from the context, you can usually pull that out. So you can get your good cluster. So then we use k-means clustering, and I actually tried spherical k-means as well. So we did that because all the word embedding stuff uses cosine distance. So that was a good way to cluster these things. So then the end result for number 5 is just like a list of topics, clusters, whatever you want to call them. And then since each transcript had dates, we were able to put those references to a time, so we know exactly when and where it was said. So with this, I plotted, I did K from 100 to 1,000 for 4 different models. So that's a mix of word-to-vec with k-means, fast text with k-means, and spherical k-means, and then also LDA. That little weird grouping right there, those are just 0 PMI. That's point-wise mutual information. So it's basically it's a context-based measurement. And you can see how in the very low scoring, the very kind of early part, that's LDA. Major majority of all the LDA clusters for all the different topic K numbers were all very low scoring. And then you can see as it goes up, the word-to-vec ones have the highest scores. I had to expand them out with some random noise so you could actually see them. So with this is actually, actually I'll go to the next one. Yeah, so here it is. This is just the average cluster score for over number of K. So you can see in the light blue, that's LDA. LDA does really good in low numbers of K. But once you expand it out, it just it tanks really bad, as I explained before. The top scoring one is, those are both word-to-vec models, and they did really well. It's a context score purely, but it's really sensitive to the number of K. So you can choose 1 K and then move up to 5 more K, and then you just get totally garbage results, and it kind of like, expands out. So down low is the pink one, pink or purple. That was the fast text spherical k-means, and that had a very, very consistent good clusters. And you can only see like a small amount of like divergence towards the end there. So actually I want to say one more thing about this. The reason why I think that the fast text scores are so much lower is because you get a lot of clusters that were like Bergdahl, Bergdorf, maybe one other like similar misspelling. But since they never actually co-occur, their PMI score is pretty low. So it's not the greatest evaluation method, but it does show a lot of critical things like robustness. Okay, so then we actually went back and we would pull out the time series for the references, and then we went to GDEL and pulled out basically the same terms that were in the cluster, and then we're just looking to see are these real or not, and we get a pretty good correlation. So when in purple, this is like the rigged system cluster. It peaks around the same time as you see a lot of news articles for rigged system. And we did another one for Romney, the choke artist, and it's a similar thing. So our time series extracted references are actually pretty reasonable compared to what you'll find if you're just typing it in, looking through news archives. So what I wanted to do with this eventually is, well, I want more robust evaluation methods that aren't just purely co-occurrence, but I'm just not aware of any. But then that would allow us to fully automate the choice of K and model all the hyperparameters, basically. And then this could also be used for any kind of messy data. So OCR data, I was thinking like public TV transcripts, all that kind of stuff. So anytime that you have like garbled information with maybe some of the letters are right, then the fast text spherical k-means could work pretty well for this. And that's it.